All right, hey you guys. Today is Tuesday, October 13th. We are going to finally finish up our last two trig functions and their graphs. I have to keep this video less than 24 minutes because that's all the storage I have left on my phone from filming all my other stuff. So we're gonna get right at it, okay? I would like you guys, just like we've been doing, I'd really like you guys to add sort of the parent graphs for cosecant and secant. You do not need to redraw these top ones or anything like this, and obviously you can feel free to pause this video at any point if you need to copy stuff down. But I do want to not just totally sacrifice the explanation of where these graphs come from. So I'm going to start by just kind of having these up here. We all know the sine graph. We know the sine graph starts at 0 and ends at 0 and goes through 0 right here, and it goes up and then down, right? Likewise, we all know the the cosine graph starts at 1, drops down to 0, gets to -1, back up to 0, and ends at 1. We all know the sine graph starts at 0, ends at 0. Cosine graph starts at 1, ends at 1. But really what I want to point out is this. We also know that cosecant is just the reciprocal of sine. So sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. It's just these are inverse functions of one another. So we're really going to think about the word inverse and especially the word reciprocal, okay? Because I want you to think about this for a second. This is going to be where this whole thing comes from. If the sine value or if the sine function is at 0 here, here, and here, this would be, okay, again, the sine value is 0 right here. But the cosecant is just at all points, it's going to be the reciprocal value of the sine function. So think about this. If the sine function is 0 right here, that means if you want to turn that into a fraction, make sure you guys can see this on my screen here. 0, if you turn that into a fraction, it's 0 over 1. So you can have 0 on top of a fraction, but what's the reciprocal of 0 over 1? That's 1 over 0, and 1 over 0 is an undefined term. So basically the big thing I want you guys to see here is this. Anywhere that the sine function is 0, its reciprocal is going to be undefined there. So what does that mean from a graphing perspective? It means the graph never gets to that point. You don't have values at 0, 180, and 360. Instead, everywhere that the sine function has a value of 0, the cosecant function, its reciprocal, is going to have a vertical asymptote. So the sine function has a 0 value at 0. That means that the cosecant function is going to have a vertical asymptote there, and then it's going to also have a vertical asymptote at 180 degrees, and it's also going to have a vertical asymptote at 360 degrees. And one thing I kind of forgot to mention was this, and you guys can add this. If the sine wave takes 360 degrees to complete, so does its reciprocal. So the cosecant function's period is back to 2 pi. Remember, tangent and cotangent, the period length is only 1 pi. Everything else is 2 pi, okay? Now, let's think about this for a second. Again, the sine value, or the sine wave, at 90 degrees has a value of 1. What's the reciprocal of 1 over 1? Well, it's still 1 over 1. So just like the sine value is at 1 at 90 degrees, so is the cosecant value. But I'm going to show you this, and I'm going to explain where this comes from. I want you to think about a point right here. Maybe that point has a y coordinate of 2/3. It's up 2/3 of a unit. Okay, we could all kind of get behind that. We're over some value, some degree length here, and we're up at 2/3. Well, the reciprocal of 2/3 would be 3/2. So that's 1.5. So at that same spot right there, instead of having a y value of 2 over 3, at that same x value, it's going to have a y value of 3/2. So what you're going to see here is this. This is actually going to be a graph that goes up. Instead of the sine value going down on both sides from here, the reciprocal of that is it's going to go up. So the cosecant curve is actually going to be between 0 and 180. It's going to be an upwards facing parabola. And then likewise down here at 270 degrees, you've got a value of -1. Well, the reciprocal of -1 is -1, so it's still down here. But instead of at that point it going up or being upwards parabolic or concave up, it's going to be a concave down parabola down here. So again, I didn't want to completely sacrifice, even though I'm kind of short on time here, I didn't want to completely sacrifice where these two parabolas come from. They're basically the inverses, meaning the reciprocals or the flips of this parabolic shape right here becomes the upwards facing one, and this upwards facing one becomes downwards facing, and that's where the cosecant graph gets its curve. What you'll notice though is, again, it takes 2 pi units to get there. A couple things that we want to mention about this one is not only is the period 2 pi, we have asymptotes at x equals, I don't even remember how we wrote this. Was it n pi, where n is an integer? I believe is how we wrote that. So at every integer value of pi, there's an asymptote. So at 0 pi, so at 0, there's a vertical asymptote. At 1 pi, there's a vertical asymptote. At 2 pi's, there's a vertical asymptote. And this continues forever and ever. There's a vertical asymptote at every pi. 0 pi, 1 pi, 2 pi, 3 pi, and so forth. But after this right here, it just repeats itself. So you'd put another vertical asymptote, and it'd be another upwards facing parabola, and then it would just keep repeating this pattern. The same concept applies over here for secant, except secant is the inverse or reciprocal of cosine. So everywhere that cosine is 0, there is a vertical asymptote for secant. So if you think about this, this was 90 degrees. At 90 degrees, there's a vertical asymptote. At 270 degrees, there is a vertical asymptote, just like this, right? Okay, and now think about this. Right here at 180 degrees, it's got a value of -1. That means at 180 degrees, this one's going to have a value of -1. Just like before over here, this concave up parabola is going to become a concave down parabola. But to get the true parent graph of the secant, what we actually have to do is we have to take our cosine curve and work backwards this way. Okay, if we work the opposite direction here, the cosine curve at -90 becomes 0. So at -90 here is where we get our other asymptote. It's kind of like the tangent and cotangent function. One of them actually has its parent graph take place from -90 to 270. 2 pi would technically be over there. So it's very similar to this. In fact, it looks identical, you know. It looks identical. It starts with a concave up parabola and then a concave down parabola. The only difference, you guys, between these two graphs is you have to remember that cosecant is the reciprocal of sine. So sine has zeros at 0, 180, and 360. That's where the asymptotes for cosecant are, 0, 180, 360, or 0 pi and 2 pi. Cosine only has, its parent graph only has 2 zeros. So to get your third 0 up here, you had to work back to -90. That's how you get your third asymptote for the parent graph. So it's just really remembering that secant is the one that goes from -90 to 270 in terms of its first period. And then cosecant goes from 0 to 360. And then, you know, kind of likewise, with this one, the period is obviously 2 pi radians, but the asymptotes are the ones that are in kind of weird spots here. Asymptotes are at x equals, now remember, this is pi over 2 radians, right? It's at pi over 2, 3 pi over 2, -1 pi over 2. So it's n, x equals n pi over 2, where you have to remember it's not every pi over 2, it's the odds. It's 1 pi over 2, 3 pi over 2, 5 pi over 2. So where n is an odd integer. Okay? All I'm really going to have time to show you guys here is probably one example. So basically, I'll go with what's a little bit weirder. Secant's just a little bit weirder because you have to remember that the asymptotes are usually at basically -1 on the x-axis, +1 and +3, even though it's actually, you know, negative pi over 2, positive pi over 2, and 3 pi over 2 radians, or whatever, however you want to think about it. But basically, here's what I'll show you. We will graph, or I'll graph this one, y equals cosecant, let's go 2 theta plus pi minus 3. Okay, what you guys are going to see is the transformations all work exactly the same way. We're going to do the same things that we were doing before. We're going to identify if there is a reflection, which obviously there's no negative out front, so we would say there is no reflection. We're going to identify if our period, the length of our period for these changes, it's the same thing. It's 2 pi. We're back to, again, the normal period's 2 pi, but now we have to divide again by this. So it's 2 pi divided by 2, so that's pi radians. But again, what does that tell us to do? That just tells us how to manipulate our first 4 units. Our first 4 units have to make up our full stretch here because every one of these, you guys, has 5 key points. In these cases, it's where you put your 3 asymptotes and it's where you put your 2 vertices for your parabolas. Again, 3 asymptotes, 2 vertices, that's 5 points. So you draw your first 4 units, pi, half of that is pi over 2, half of that would be pi over 4. So it's 1/4 pi, 1/4, 2/4, 3/4 pi, 4/4, 5/4, 6/4 would be 3 pi over 2. I'll keep going here. 6/4, 7 pi over 4, and then 8 pi over 4 would obviously be 2 pi. Now, I'm probably going to have to work back this direction just a little bit, but we'll deal with that in just a second, okay? Let's identify any phase shift, any vertical shift, and our amplitude for all these is going to be 1. I think I adjusted these so that the amplitude's always 1. Okay, phase shift is the same. It's the opposite of that, so it's negative pi over whatever this is, so it's just negative pi over 2. Okay, we'll talk about that in just a second. All right, you guys? Move my x-axis back this way just a fuzz. There is also a vertical shift of -3, so we'll talk about that. We're going to have to shift our graph down a ways. I may need to extend my x-axis here. All right, at any rate, what you have to think about now, oh, you know what? I actually wanted to do, instead of cosecant here, I apologize. I wanted to do secant because secant, again, is the one where your vertical asymptotes are at -1, -1, 1, and 3. So, if I'm thinking about this, I would need to scale back here to -1. That would be negative pi over 4. Now think about this, you guys. For secant, the vertical asymptote's usually at -1. I need to slide that negative pi over 2 radians. So think about that. How many actual marks is that on here? Pi over 2 radians on here is 2 marks. I need to slide this vertical asymptote back 2. So it's actually all the way back at -3 on my x-axis. And if I'm going to go that far, I should probably label it. So this is negative pi over 2. This right here at this asymptote would be negative 3 pi over 4. From there, though, really all you have to remember is what is secant made of? It's made of 3 asymptotes. So there's one, here's my next one, and then here's my next one. These 3 asymptotes are gonna make up my first period, so I'm gonna have to do another period here. But think about this. All I have to do is draw from my midline, and I can move my midline now, because remember, my midline is usually my x-axis, and my parabolas are one above and one below. But now my midline is gonna slide down 3 units. So I put here's 1, here's 2, here's 3. Here's my new midline. Kind of gets a little bit messy here. But from there, now I can go from my midline up 1, put a dot there, draw a parabola. Then I can go over here, I'm at 0, down 1, put a dot there, draw your inverted parabola. And then all I have to do is basically replicate that for another period. So go over 2 more marks on my x-axis, draw another asymptote, 2 more marks, draw another asymptote. In between these 2 asymptotes, go down to your midline, up 1, put a dot, draw your parabola. In between these 2 asymptotes, go to your midline, down 1, draw a dot, and then your inverted parabola. It's just a matter of remembering, where are my asymptotes? My asymptotes are at -1, 1, and 3 for secant. For cosecant, they're at 0, 2, and 4, regardless of what the scale of your graph is, okay? So you really just have to kind of keep that mental balance of bouncing back and forth between where are the asymptotes in terms of what actual tick mark, left one, right one, stuff like that. And then remembering that you're also talking about a scale adjustment for any of these period shifts, okay? So it's just about labeling your x-axis and then being able to think from there where these things should go, okay? So I'm gonna have you guys try this today. In all likelihood, tomorrow we probably won't really move on. We'll probably just kind of re-explain some of this. I might go through, and if you guys send me individual questions, I might go through some of those questions tomorrow. But in all likelihood, what we're probably gonna do is 2 different worksheets. One maybe just on cosecant and secant, and then we're gonna start blending all this stuff back together. Sine, cosine, cosecant, secant, and tangent and cotangent, because relatively soon, you guys, probably right when we get back together next week, we'll probably be to a point that Monday or Tuesday where we're going to take a quiz on just all these different graphs of these transformations of these trig functions. Okay, so definitely today, shoot me your questions. Let me know if there's any of them that you're particularly struggling on. And if you're, to be honest, if you're just struggling on them entirely and you just can't get it going, then just hold off, wait till tomorrow. Like I said, I'm probably just going to kind of re-explain some of this stuff, show a few more examples when we have a little bit more time tomorrow, and hopefully that'll clear up any confusions. And then we can start putting this stuff all back together. All right, guys, have a good day. Like I said, shoot me any questions you have if you have particular ones, and we'll finish this off, and then we can start putting it all together. All right, we'll talk to you later.